Greetings. So welcome to today's class. So let's continue from where we left off in the previous class. So if you recall, we were looking at the state space representation, and we saw that the basic idea behind the state space representation is to rewrite this nth order ODE as n first order ODEs, and then essentially formulate what are called as the state equation and the output or measurement equation, right? So that is the basic idea. And we saw that for a typical single input, single output linear time causal dynamic system, the state equation takes the form x dot equals ax plus ba, and the output equation takes the form y of t equals c dot x plus ba. Right? And then we discussed an equivalence between the Planck transfer function and the state space representation. So P of S will be C dot Si minus A inverse B plus D. And I gave you an exercise to do to essentially check this expression for the mass spring damper system. So what we will do to begin with today is to essentially check that, okay? Do that problem for a mass spring damper system, so that like we can gain some insight from that, and then like we will continue the discussion. Okay, so let's do that exercise problem. So the exercise problem was for the mass spring damper system, and for the mass spring damper system, Si minus A will take the form S minus 1 K by M and S plus C by M, right? So we just we'll get this. Now, how did we get this? Because we already had A, right? A was 0, 1 minus K by M minus C by M, right? Which we already knew. Yeah. So here is the matrix A, right? 0, 1 minus K by M minus C by M. So we just subtracted from this times identity. So this is what we get. So as we know the inverse of a matrix, we need to take the inverse of Si minus A, right? The inverse of the matrix will be the adjoint of the matrix divided by its determinant. So if we evaluate the determinant of Si minus A, we would see that we will get the equation to be S times S plus C by M. Since it's just a 2 by 2 matrix, we multiply the diagonal elements and take the difference of the product of the off diagonal elements, right? Which will be this minus 1 times K by M. So we will end up with S square plus C by M S plus K by M, okay, which can be rewritten as 1 by M multiplying MS square plus CS plus K, right? That is going to be the determinant, right? So now, if we take the adjoint of this matrix Si minus A, how do we get the adjoint of a matrix in general? We formulate what is called as the cofactor matrix, and then we transpose the cofactor matrix, right? So in this particular case of 2 by 2, what we need to do is form the cofactor matrix. We just swap the entries. So S is swapped with S plus C by M. Okay, minus 1 is swapped with minus K by M. We need to change the symbol, okay, of this term, and then K by M gets replaced with plus 1, okay, and S plus C by M gets replaced with S. So then we need to take the transpose of it. So if we take the transpose, we interchange the rows and columns. So we'll get S plus C by M 1 minus K by M and S. Okay, so this is what we get. Okay, and how do we get the cofactor matrix in general? It is a signed minor, right? So what is a minor? A minor at the ijth element is going to be you remove the ith row and the jth column. You get a n minus 1 by n minus 1 matrix. You take the determinant of that matrix, right? So that's how you get the minor. Sign minor means you multiply that value by -1 to the power I plus j. Okay, so that is why we get what to say signs, right? The way they are, right? So in this particular expression. Okay, so this is the adjoint of that matrix. So as we discussed, the inverse of Si minus A will now be the adjoint of Si minus A divided by the determinant of Si minus A. Okay, so if we do this, we will immediately see that we will get m divided by ms squared plus cs plus k. This would be multiplying s plus c by m 1 minus k by m. Yes. So this will be the inverse of that matrix. Okay, si minus c. Okay. So now what we need to do is we need to take S I minus A inverse times B and then like multiply the vector which results out of that with C dot. C, right? Take the dot product. So let's calculate C dot Si minus A inverse B plus D, right? So C in the case of the mass spin damper system is 1, 0. That is a column vector. Si minus A inverse, we have got it as M divided by that is a scalar function. So like this, and we are going to have S plus C by M 1 minus K by M and S, right? And B was 0 and 1. So how do we do the matrix multiplication? First, we essentially multiply this matrix and this vector. We will get a vector, right? And then we need to take the dot product of that with 1, 0. So since m divided by ms squared plus cs plus k is a scalar value function, we can take it out. Okay, and then what we would be left with is 1, 0, which is a column vector C dot product with the matrix multiplication of this 2 by 2
Sorry,
matrix.
sir.
Yes, please.
So 1, 0 value for C, how are we taking it? Are we considering it a kind of mass spring damper system?
Yeah, I'm doing the problem for the mass spring damper system, right? So if you recall,
okay,
this is
yeah.
something we did, right? So we got the output vector as 1, 0, right? So, right?
So this value can change, right? The value of C based on different.
Yeah, obviously, depending on the output, the value of C will change. You are correct. Yeah. In this example, we have taken displacement as the output, and that's how we calculated the transfer function, right? Was it wrong?
Yeah. Oh, okay, sir. Thank
you. So going back for the mass spin damper system, we are visualizing it as a system for which force is the input and displacement is the output, right? So that's why we are doing this. Right? Okay, so we got 1, 0 as the value of the vector C. And if we take the matrix multiplication of this 2 by 2 matrix with the column vector 0, 1, we will get 1 by M and S by M, right? That's what we have. Okay. Now we need to take the dot product of these two column vectors, right? So if we take the dot product of these two column vectors, what will we get? We'll get M divided by ms squared plus cs plus k. The dot product will just be 1 by m, right? Will it not? Because the second element is 0, right, in the first column. So we just get 1 by m. And this m and this m will get cancelled. Consequently, we will be left with 1 divided by ms squared plus cs plus k, which is nothing but the Planck constant. Okay? So you can see that we have indeed checked or verified that equation. All right. So I hope it is clear how we check, right? So in general, for a single input, single output, SSO causal dynamic system, the the relationship between the state space realization and the plan transfer function is going to be of this particular form. All right. Okay. So now, if you look at the plan transfer function, I hope this example was clear, right? So how we checked it for the mass frame damper system, right? Yeah. So now, if you look at the transfer function, all of us know that the transfer function is going to be a ratio of two polynomials in S, right? M of S divided by D of S, and we see that we just also observe that the inverse of Si minus A is going to be the adjoint of Si minus A divided by the determinant of Si minus A. Okay, so that's what it will be. So immediately, if you look at the two sides and look at the denominator, the denominator on the left hand side will be D of S, right? So the roots of D of S or what are called as the poles of the transfer function, right? The roots of the polynomial d of s are nothing but the poles of the transfer function p of s. In the the right hand side, we have determinant of Si minus A in the denominator, and the roots of determinant of Si minus A, what are they called as? They would be the eigenvalues of A, right? So if you recall, in the end of the previous class, we discussed about eigenvalues and eigenvectors, right? So of course, I used lambda, okay, but you can use any general complex symbol also, right? Yes. So the way we calculate eigenvalues is by solving the determinant of lambda I minus A equals 0. So here, what we do is that, like, if I want to figure out the roots of Si minus A, we have to solve Si minus A equal to 0. So essentially, the values of S which we get by solving this equation would be the eigenvalues of A. All right. So this gives us a very, very important result. Okay. So we will learn what this minimal realization is later. Okay. For a so-called minimal realization, the eigenvalues of the state matrix A are the same as the poles of the transfer function P of x. Okay, so for what is called as a minimal realization, the eigenvalues of the state matrix and the poles of the transfer function are one and the same. All right. So that can be easily observed for a mass spring damper system, right? Because in both cases, we need to solve ms squared plus cs plus k equals 0. All right. But we shall learn later what is meant by this minimal realization. All right. Okay. So is this example clear? The follow-up concept?
Yes, sir.
Okay. So now the next sort of like concept that I'm going to discuss is about solutions to ordinary differential equations. Why are we going to look at solutions to ordinary differential equations? Okay, because if you look at, see, let's connect all the things, right? So in practice, we are going to have what to say, system models, right? We take any system or a process, let's say we approximate it as a linear time invariant system. Then what we do is that, like, we are going to get linear ordinary differential equations with constant coefficients, right? So if we do that, what's going to happen is that, like, we are going to get the state space representation in the form shown here, right? X dot equals ax plus bu, y equals c dot x plus b. So once we get that, like we should be in a position to solve the differential equation, right? Only then we can get the states. Okay, so that's where ordinary differential equations and the solution become very important. Simplification that we obtain is that like we are only going to consider first order ODEs, right? So we will consider first order uh, linear ordinary differential equations with constant coefficients. Okay, so that's the scope of our discussion. Why are we considering only this class of ODEs? Because that's what we are going to get, right? Based on our approach, right? So we are going to get linear first order ordinary differential equations with constant coefficients as a class of equations for our problem. So that is what we will be considering. Okay, so let us first consider, okay, a very simple equation. Okay, we will consider scalar only. Okay, we'll start from simple examples and go progressively to a more say general cases. Okay, so if you consider a simple example, this is a linear first order homogeneous ODE. Okay, so this is a linear first order homogeneous ordinary differential equation. So the reason why it's called linear is obvious to all of us. Why it's first order is also obvious to all of us. Why do you think it's called homogeneous?
The forcing function is not there.
Very good. So in fact, if you rewrite this equation as x dot t minus axt equal to 0, as Ramkumar correctly told, the forcing term is not present, right, on the right hand side. Okay, so that's why it's a homogeneous ordinary differential equation. So, and if we consider its solution, it is well known that the solution to this class of equation is going to be x of t is going to be x naught e power a. Okay, the solution to this particular equation.
So x of 0 is a constant.
X of 0 is an initial condition, correct. It is. It should be provided. It's an initial value problem, right? So what is x of 0? X of 0 is initial condition, okay, which is a constant parameter. Because we are considering problems where time is the independent variable, right? So x of 0 will be the value at t equals 0. Okay, that is what is called as the initial condition. Right? Now let us consider the vector equivalent of this. So what are we going to consider now? Let's consider case where x dot t is equal to a times x of t. Okay, where you can see that it's still first order, it is still linear, it is still homogeneous, but it's a vector ODE, right? So is linear first order homogeneous vector ODE. Okay, so and you can see where we are coming to, right? Because if you look at the state space representation, we had, if you recall, we had x dot t equal to axt plus but, right? That was the state equation, right? Was it not? We are not considering the forcing term. Okay, this is the forcing term. Okay, so we are not considering the forcing term here. That's why it's homogeneous. We are looking only at the homogeneous component of this particular equation. Okay, so this is what's called as a homogeneous ODE. All right, the linear first order homogeneous vector ODE. Right. So now, this, let us say we take the Laplace transform on both sides. Okay. So if you if we take the Laplace transform on both sides, what we are going to get for x dot, we will get s of x of s minus x0. Okay, that's going to be equal to a times x of x. Okay, so we are going to use the same formula, right, for the Laplace of the derivative, although the derivative is a vector derivative, right? So that's what we are going to have. Now, if we group the terms of capital X of s, we are going to get si minus a x of s. That's going to be equal to x0, right? So, if we look at this, and if we take the inverse of si minus a, so x of s we will get as si minus a inverse x0. Okay, so if we take the inverse Laplace transform of this equation, so if we take the inverse Laplace, you will get x of t, right? You will get x of t to be some phi t x0, and where what is phi t? Where phi t is the Laplace inverse of si minus a inverse. So we have this quantity si minus a inverse. What we do is that we have to take the Laplace inverse of this quantity, and then we get a quantity called phi t. Okay? How do we get this? We'll discuss shortly. Okay. So we are going to look at that. Okay, but I hope the process is clear. So what we have done is that, like, we have essentially taken this vector first order linear homogeneous ODE, right, and obtain the solution to the ODE as some x of t to be phi t x0, where phi t is its Laplace inverse of si minus a. Okay, so that's what we have obtained, right? So please keep this in mind. Okay, we are going to revisit this, right, and we will see what this phi t is and how do we get it, right, in practice. Okay? So that's something we are going to look at shortly. Right. So in order to evaluate this phi t, we are going to essentially consider what is called as a matrix exponential. So what is this? Let us consider some psi t, some function psi t to be equal to e power a t. Okay, this is known as the matrix exponential. Okay, so of course we would have encountered exponentials of a scalar variables, and that would have resulted in a scalar valued function. Now we are taking an exponential of a matrix. Okay, we are taking the exponential of AT, and that's why it will be a matrix exponential. So the result is also going to be a matrix. Okay, so that's why it's called as a matrix exponential. Okay, so what are the few properties of the matrix exponential? I'm not going to prove them. I'm just going to present to you what some properties are, and we will be using these properties shortly. Okay, as we go along. So a few properties that are useful to us, right, as far as this matrix exponential is concerned. The first property is that if we take the time derivative of the matrix exponential, here went again, a times e power at, which is also equal to e power at multiplied by a. Okay, so this is something that's very important. Why is this important? Because please note that matrices do not commute in general. Okay, under multiplication. So if you take two matrices A times B, A times B is not going to be equal to B times A in general. So please recall our notation. So for matrices, typically we use uppercase boldface font. So while for writing on the screen, I am going to essentially consider a tilde underneath the the character, okay, to denote that it's a matrix. All right. So this is one property. So if we take the time derivative of this matrix exponential, we are going to get a times e power at, which is also equal to e power at times a. So that is one form. Then the second property, which is going to be useful for us, is that time t equals 0. Okay, so if we evaluate at time t equals 0, so we are going to get the identity matrix. Okay, so that is a second property. Okay, so of course one may think, hey, these look very straightforward, right? Because we are used to such results from scalar valued exponential functions. But these know that these are matrix valued functions. Okay, so these results are useful. All right. So another, as I told, I'm not proving that. Another property is that, like, if we have e power at times e power a tau, there are two different time instances. The answer is going to be e power a t plus 1. Okay, so that is one property. And if we have e power at multiplied by e power bt, that's also going to be e power a b plus b. Okay, so once again, like from an experience with you know usual scalar value matrix functions, these seem very obvious, but as I told, these are matrix exponentials. Okay, so that's why I'm reiterating some of the properties. And if we have e power at times e power minus at, so we are going to have identity. All right. So this follows from property number 4 and 2. Okay. So immediately we can observe that the inverse of e power at is going to be e power minus at. Okay. So that's an important property. Okay. So once again, please note that these are not very straightforward because we are dealing with matrix exponentials. Okay, so that's why these are useful properties. Okay, so now having learned these, yeah, any questions?
So, sir, what is that A0?
A0 means time t equals 0. The 0
okay.
means
Got it.
substitute t equals 0, right? The initial condition, initial time. Right?
And T and tau are different
Are
quantities?
two different instances of time, right? So two different scalar quantities.
Oh, they both represent time, but at two
Time,
different.
yeah, two different. You can, let's say, if let's say like p and tau are sort of like confusing, we can say t1 and t2.
Oh, okay.
Let's say instance of time. Okay,
Yeah.
right. I hope this is clear.
Yes,
Okay.
sir.
Yeah. Any other questions?
No.
Yeah. Okay. So the question is now, how do we evaluate? See, all this mathematics is fine, but ultimately we need to use it in practice, right? How do we evaluate this e power 8? That's an important question, right? So one method is to expand it. See, we know from basic mathematics that there is a power series expansion for exponential functions, right? Similarly, for matrix exponentials also, there is an infinite series expansion. So e power 80 can be written as I plus a times t plus a squared t squared by 2 factorial, right? Plus all the way to a power k t power k divided by k factorial plus 1. Okay, so that's how we evaluate the matrix exponential, right? It's very analogous to what we have, right? As far as even the scalar valued exponential function is concerned. Okay, so we use a similar series expansion, right, for a matrix exponential. Okay. So, but once again, this is not also like very useful in practice, because how do we evaluate an infinite series expansion, that too when matrices are present? Okay. So another method which is very commonly used, and I'm going to link it with what we studied a few minutes back, is the following. Okay. Let's consider a function, let's say f of t, which is a matrix valued function, which let's say which is e power at, right? So since we just learned that the derivative of the time derivative of e power at is going to be equal to a times e power at. This is something which we just learned, right? So we can immediately see that the time derivative of d of dt, this function, what we call as f, is going to be equal to a times f of t, right? So I'm just substituting for e power at that f of t. Okay? Just a notation, okay? Just a substitution as a symbol. Okay? And please note that f of 0, which is nothing but f of t evaluated at time t equals 0, will be e power a0, as we have already seen from the properties. It's going to be identical. Okay? So please remember this also, right? So now let us take Laplace transform on both sides. Sorry. Let's take the Laplace transform on both sides. So both sides of this equation, df dt equals af. Okay? If we take Laplace transform, we are going to get s times f of s minus f of 0. Right? That's going to be equal to a times f of s. Okay, so f of 0, as we know, it's going to be identity. So if we simplify this expression, we are going to get si minus a times f of s is going to be equal to identity. Correct? So we just swap the terms between the two sets, right? So then we get si minus a f of s equal to identity. Then what we have, sorry, then we have that f of s will become si minus a inverse. Right? Because si minus a inverse times identity is going to be si minus a itself. Right? So now let's take the inverse Laplace transform on both sides. If you take the inverse Laplace transform on both sides, what are we going to do? If you take the inverse Laplace transform on both sides, we are going to get f of t. But f of t, we know that it's e power at, right? How do we know it's e power at? Because that's what we started off with, right? So that's going to be equal to Laplace inverse of si minus a. However, what was Laplace inverse of si minus a inverse?
Pi of
If
t.
we, yeah, we just learned that it's phi of t, right? So if I go back, yeah, it is phi of t, right? That's what we learned here, right? So if you can, right? So Laplace inverse of si minus a inverse is going to be equal to phi of t, right? So we have got something very, very interesting, right? So what have we done? By considering this matrix exponential e power at and by using the properties of the matrix exponential, we have obtained that the quantity phi of t, which comes in the solution, right, to that vector homogeneous first order linear differential equation x dot equals ax is in fact x of t equals e power a t x, right? So this implies a solution to x dot t equals axt is x of t is equal to e power a t x. Of course, one may say, hey, look, isn't this very straightforward? You know, like this is how it came for the scalar equation also. And that is exactly the point, right? Because now we are dealing with a vector ODE, right? So what to say, whatever we learned for the scalar ODE, sometimes it may look that it is directly applicable, sometimes it will not. Okay, so we need to be very careful. All right. So, but please note that I can't swap e power 80 and x0 here, right? Because e power 80 is a matrix, x0 is a vector, right? So we can swap the order of multiplication. Okay. So immediately you can see that there are some differences, right, that come into play. All right. And this quantity Si minus A inverse, oops, what happened here? Sorry about that. Okay. The quantity Si minus A inverse is what is called as a resolvent matrix. Right? And e power 80 due to this reason, because it comes in the solution to the equation, it is what is called as a state transition matrix. So why is it called as a state transition matrix? Because please note that if you recall the starting point of our discussion, we are looking at the state equation, right? X dot t equals axt plus bu. Of course, we have not considered BUT yet. We will consider it shortly. But if we consider x dot equals axt, which is the homogeneous part, we immediately observe that the solution has is essentially x of t equals e power a t x0. So we can observe that the solution to the state, right, has this matrix exponential e power a t, and for that reason, e power kt is what is called as the state transition matrix. Okay, and the reason why it is called as a state transition matrix is also because it is sort of like mapping the initial state, right, to the state at any instant of time, right? So you look at this equation, it is x of t equals e power at x of 0, right? Is it not? So what we are doing is that like we are essentially mapping the initial state x0 to any given state or the state at any given time. Okay, so that is why it is called as a state transition matrix. Fine. Okay. Any questions on this? Or so now we are progressing, right? So we are slowly getting to the solution to the state equation. Okay, in the next class we will look at the solution to the non-inhomogeneous part. We will see what happens with that. But before we go there, right, what I'm going to leave you with as an exercise from today's class is the following. Okay, this is an exercise problem. So you consider the matrix A. Let us say the matrix A is 1, 2, 0. Okay, so what I want you to find is find e power. Okay, using this Laplace inverse of Si minus A. Okay, so you can essentially find Si minus A and take its inverse, and then you can find its Laplace inverse. Okay, then you will be able to find e power 8. All right. So I can straight away tell that the solution is not going to be. You think the answer is going to be this? We are mistaken. Okay, so it's not going to be the what to say exponentials of the individual terms. That may be the case in some special cases, but this is not the answer. Okay, so if we think, oh, okay, I can get e power at by taking the exponentials of the individual entries in the matrix, okay, we will get an incorrect answer, right? So that's not going to be the correct answer at all, right? That's why we need to evaluate this resolvent matrix and take its Laplace inverse to get the correct answer. Okay, so please try that as an exercise problem. We will discuss in the next class. And then we will continue with our discussion on obtaining the solution, right, to the state equation with the input term, okay, which will be the complete state equation with the inhomogeneous term also coming into the ODE, right? So that's something we'll discuss in the next class. So any questions about what we learned in today's class? Okay, so if not, we
Sir,
stop.
one question.
Yeah, please go on.
The last, can we go to the notes? The last line that.
Sorry. Yeah. Yeah.
So, okay, the final line that says the solution to x dot t is equal to axt whatever. So, have you implied it from the previous derivation? Or
Yes, because see, what is the first step? First, we figured out that the solution is this: x of t is phi of t x0, right? Isn't it? That was step number one, correct?
oh
Right?
yeah. Yes.
Then in this derivation, we have figured out phi of t is e power at, right? I'm just substituting for phi. That's it. I hope
Phi.
it's clear. Yeah.
So we got phi of t equals to.
Right. Yeah.
Right, sir.
So
Yeah.
yeah, if you look at this step, we have got phi of t to be e power at, right? Isn't it? So that's what.
Correct.
Right. So I just substituted. That's it.
Yeah, got it.
Correct. Yeah. So yeah.
Thank you.
Any other questions? Okay, so let me stop.